The last thing we did is I wrote up the linear rotational analogs, and we talked about how to create new equations. Is that the last thing I did? Or am I confusing with a different class? Or open it up to, what was the last thing we did?
That's the last thing I have on my notes is the.
Okay.
I think that's right.
Let's talk a little bit about torque. Not capitalized for any particular reason. All right, so we got two different aspects here. Magnitude and direction. So let's talk a little bit about how do you define the direction of things that are spinning. So we'll start out with the wheel. How would you describe the direction of the spin? Okay. Thank you.
To the right.
Pardon me?
To the right.
Why to the right?
To the left. Sorry.
Why to the left?
Clockwise?
Yeah. Clockwise.
Right, to the right or to the left is, because from my point of view, that's going this way and that's going that way. I think we all agree that that's going that way and that's going that way. But clockwise? I would have said counterclockwise.
Yeah.
So how could you define it a little bit better so that it's less confusing?
Rotational?
Well, that's sort of where we're heading, but
Like, superior and anterior, but I'm not good at that, but I was thinking like, since you're, I can't even do that, because you say you're in that position too, so.
Could you just say like clockwise from where I'm standing or counterclockwise from where you're standing?
and oftentimes that is what's done. However, that then you have to describe the general landscape. I mean that. So when you're in room Ardmore 231 at Forsyth Tech in Winston-Salem, standing in the middle of the room, it was spinning clockwise. That's a mouthful. So the powers that be came up with something that sort of a convention for it. It is what's called a right-hand rule. There's actually several right-hand rules in physics. This is one of the right-hand rules. It is not the dominant hand rule. So if you're left-handed, it's still the right-hand rule. Can we all pretty much agree that there's an axle here, that it's spinning about this shaft? Does anyone want to debate that? All right. So as it's spinning, the right-hand rule is you basically treat your thumb as the axle. And so that means, so that's going to be pointing along the direction of the axle, which means it's either going that way or that way, because there are only two different ways it could go. If that's the case, you want your fingers so that when they sort of naturally curve, they will curve in the direction that it's spinning. So as it's spinning like this, my thumb is either going to be pointing out or in, towards the back of the room or towards the front of the room. And then I want my fingers to sort of curl in the same direction that it's rotating about the axle. So, unless you're taking notes on your computer should be shut. So in that case, when it was spinning from Andre's point of view, clockwise, the thumb would be pointing towards the front of the room. And so the convention they came up with is that the direction of the rotation is towards the front of the room. That way, no matter, granted, we're still dealing with this room, but it doesn't matter whether you're standing on that side of the wheel or this side of the wheel. If the direction is towards the front of the room, I know it's spinning around like this. What's the direction of that rotation? Let's be more official.
Towards the back of the room?
Yes. What's the direction of that? The thumb's either pointing up or pointing down, because that's the axle.
Towards the bottom of the room?
Down, is that what you're saying?
Yeah.
Okay. Yeah, because it's spinning around like this, so if my fingers are gonna curl around in that direction, my thumb has to point down. Now, if I close that door, what would be the direction of the rotation then? Still doing right hand rule.
When it's I mean, the door doesn't make any difference, right? You
Where
sure?
would the?
It's still rotating about some central point, so your thumb, what's the axis of rotation for a door?
Is it the hinges?
Yes, and the hinges run vertically, so that means my thumb's either pointing up or pointing down. So if the door is being closed,
To the top?
Sorry.
Or top of the room?
okay, ceiling
Yeah.
or up, yeah, or top of roof, I mean, what you said isn't wrong. Yeah, because if my thumb is at the hinge, if I treat this as a hinge and I have the doors rotating around like that, it is, in the long run, a whole lot easier than going, well, if you look at the door from the top point of view, it's rotating counterclockwise. It's just easier saying that the rotation is up. So that gets into direction of torque. All the rotational things pretty much work the same way. Now, because this is an academic class, what we're gonna do is we're going to analyze how to actually close a door. It is something I'm assuming all of you have done most of your lives. And so therefore, let's figure out what exactly is going on. So what I'd like you to do is tell me, what do I need to do to close the door?
Rotate it.
So if I rotate the door
Towards the frame of the door.
towards what?
Towards the frame of the door.
Rotate it towards the frame of the door. I tried to get it towards that front part of the frame right there. Didn't work. Or I could have gone into how do you actually rotate.
You rotate it up, it's like your thumbs.
Okay, so I want to rotate it up, so how do I actually do that? Go on, all of you have closed the door before. What do you do?
Just push it.
Ah, push on the door. Didn't quite work.
On the back side.
Like, side?
No, the other side.
This is the back side.
Yeah.
Why is that the back side?
Because it just is. I don't know.
Okay. All right, so one thing that's important there is one, I have to push on it. So if I'm pushing, what am I applying?
Force.
All right, so I've got a force being applied. Where I apply the force matters. So that's something we need to take into account. Now, if I want to close it efficiently, so let me get at least part way so I got some room here. So what I've gotten so far is I need to push on this side of the door. Does it matter where I push on this side of the door?
Yeah.
Why? What?
Not really.
Not really.
If I want to do it efficiently.
Push closer to the
Close.
doorknob,
Closer to the doorknob than where?
like
In the
near the
hinges.
hinges.
Okay, so the farther I am away from the hinge,
Yes.
all right, so I'm gonna push closer to the doorknob, far away from the hinge. Wasn't particularly efficient there, it was closing. How could I push more efficiently?
Keep your hands on the.
I didn't quite hear.
I was saying keep your hands on the door, but you gonna do something,
I mean, my hand's on the door there. Still not the most efficient.
You have to push in like the direction that's, not sideways.
Push toward the hinges.
Push towards the hinges?
Yeah, see what that does. No, from the back, or,
Back to where I am. Push towards the hinges. Push that way.
oh, God, never mind.
Years ago, I did an exercise about how to tie a shoe. That was a lot of fun. First, I had to figure out whether to go in one rabbit ear or two rabbit ear method. Oh, so close to this last little piece.
Could you push perpendicularly?
There we go. There's a nice key word. All right, so there's three major things involved here. One, force. And fading markers. That's slightly better. So force matters. Where force is applied matters. This is called, I think Hewitt calls it the lever arm. I have a tendency to call it the moment arm. Again, moment showing up again. Think of moment of inertia deals with rotation. And angle of push. These are the three things that matter when you're trying to figure out about what's going to cause something to rotate or stop rotating, just like a force can cause things to accelerate or stop it, or stop moving.
Did you hit record? I can't tell.
I think I did. It is recording.
Okay.
So naturally, physicists took these three concepts here and they bundled up into as few letters as possible. Boom, there we go. That's the fewest letters as possible. This R tells you how close you are to the axis where you're pushing. The F tells you how much force you're applying, and this X deals with the angle. When you're multiplying vectors, there's two different ways. One is a dot product, which we did when we talked about work, and this one's called a cross product because you have a cross right there. Aisha. Thank you. A cross product, when you do a cross product, you end up with a vector. Unlike dot products where you end up with a scalar. Now, if the angle between the moment arm and force is 90 degrees, then the magnitude of the torque is you just multiply the moment arm times the force. So, for example, this is a door, overhead view. And we'll make the door 1.5 meters long. And you push perpendicular here with 30 newtons of force.
What is that between the R and that?
Between that's my shorthand for and. So the magnitude of the torque. Since this is perpendicular, the force is perpendicular to the moment arm. And the moment arm, let's make that official. Moment arm is a vector from the hinge, or from the axis of rotation to where the force is applied. So that would be R. It's a vector, because of course it is. From axis of rotation. In the case of a door, the hinge, I hope. If a door does not rotate about its hinge, then you either got something funky or there's something wrong, really wrong. The wear force is applied. So in this example, the force is perpendicular to the moment arm, or the lever arm. And so the magnitude of the torque is just 1.5 meters times 30 newtons, which is 45 somethings. What are the units?
Newton meters?
Absolutely. However, like give people a chance to catch up and write it. If I push on a box with 30 newtons of force and I'm pushing in the direction of movement, and the box moves 1.5 meters, how much work did I do?
45 joules. 45 joules, right?
Yeah, okay. So I do 30 newtons times 1.5 meters, and I get 30 newton meters, which is 30 joules. When dealing with work and energy, a newton meter is a joule. This is absolutely correct. When dealing with torque, a newton meter is not a joule. This is one of those unfortunate things. You happen to be multiplying some distance times some force. The units both are newton meters. However, this is a joule, this is not.
So what is it actually?
Pardon?
What is that? Is it just newton meter?
Just newton meter.
Okay.
Wait, for the box, is it 30 joules or 45?
Oh, yeah, 45, I'm sorry.
Oh, okay. I was just wondering if I was missing something.
Nope, that was like Carol says. I think Hunter said 45. Yeah, I misread it. Now, in this particular case, what is the direction of the torque? I see one person pointing in all sorts of directions.
Do you mean in terms of like north, south, east, west?
Or back of room, front of room, towards the bathroom, towards the outside. I guess that's big. Towards the back of the room or towards the front of the room, towards
Are you
that side to
gonna-
that side, that's up or down.
Are you gonna use iHat for that?
Do you want to? I hat, J hat, and K hat. When you have to do 3 dimensions, something like that, I and J we've had no problem with, but now we actually are into 3 dimensions. When you see the dot, that indicates coming out. If it's going in, this would be into the surface. This is out of surface. The memory trick is, think of an arrow. If an arrow is coming at you, you see the point. If it's going away from you, you see the feathers. I know archery feathers are not shaped like that. It's a memory thing. So in this case right here, there's the dot, so it's coming out that way. All right, so the direction of the torque. Just quite sure which way you're pointing, Andre. You're going at that way? That, you're going at an angle, sort of, somewhere in between here. No. Anyone else? Are we we take Andre's word for it. The faith that they have in him, it's incredible. Which way will that force cause the door to spin? Let's do it in terms of clockwise, counterclockwise for right now, since we're all on the same side of it. Which way would that force cause that door to spin?
Counterclockwise?
Counterclockwise.
All right, counterclockwise. Around like that. Remember, the thumb is along the hinges. Overhead view, my hinges, my axis is basically going along this line right here. And so the direction of the torque is the back of the room. Or the K-hat direction. Yeah, again, I assure you, in the long run, it's a whole lot easier to do it this way. I think you're basically pointing in the direction of the lever arm. The direction of the lever arm definitely is in that way, that direction.
Wait, is it, negative K hat if it's the other way?
Yes. So if that 30 newtons flipped around over here, that would cause the door to rotate clockwise. So that would be 45 Newton meters, sorry, negative 45 Newton meters K hat. Again, you traditionally put the negative sign in front. All right. So this is how you do an individual torque right here. So this is the formula for individual torque. However, if you've got a whole bunch of torques, or you've added up all the torques acting on an object, the total torque is related to F equals ma